Welcome to the lecture on conservation of momentum. So again, this should be um, conservation of momentum itself is there's not many problems that you can do. Well, there's a lot of problems you can do with it. I tend to not ask a lot of problems having to do with it. I tend to spend more time on collisions, which will be 2 lectures from now. But anyway, so we'll just jump right into it. So most of these should be kind of small, short lectures. So conservation of momentum is, I've said before, almost more important than conservation of energy. That's just my opinion. But it really, what it makes do, just how we saw how the forces dealing with the impulse and momentum in the last lecture, these problems are really cut and dry, and they make problems solvable that otherwise would be almost impossible to do using Newtonian mechanics. So it's really the whole purpose of going into conservation of momentum and impulse itself is it lets us, or it gives us access to being able to solve a different type of problem that we otherwise wouldn't be able to. So anyway, so with conservation of momentum, all it says in words is in the absence of external forces. So that means no external forces. The total momentum of a system or object will remain constant. So basically, this is a restatement of Newton's first law of motion, where instead of velocity, the whole an object at rest stays at rest, and an object, moving in a straight line will continue on, blah, blah, blah. If we just replace velocity, all we're doing is taking the velocity and multiplying it by a mass, and now we have a momentum. So it's really just a restatement of that. Okay, so we saw in the last lecture with impulse and momentum that we had that, average force was equal to delta P over delta T. Well, we're just saying now that, oh, well, what if every force that we talked about in the last lecture was an external force? We had a bat coming in and hitting a ball, or we had a kid come up and kick a ball. Those are external forces. So you could just say, okay, well, if the external force was zero, then the momentum would not change. Well, duh. So this is the law. This is where it comes from. So we just have it simply, it looks very deceptively simple. It's just delta P is equal to zero. Well, delta P is not always equal to zero, but in the absence of external forces, it's equal to zero. And so you'll find that this is very useful for collisions, which we'll get to in the next lecture, or 2 lectures from now. And there's a few types of problems I typically like to ask dealing with momentum conservation. So we'll just go right ahead. We have 3 examples. So the first example that we'll have is a bullet being fired from a gun. This could work for a cannon. This could work for basically anything that initially has no momentum. And what happens, or what has to happen if a projectile is shot out or thrown or anything. Okay, so if anyone has ever fired a rifle and made the mistake of not having it seated against your shoulder, you know all about recoil speeds of rifles and guns. So this is to show why that happens. Okay, it's purely a consequence of physics. So first example, so we have let's say it was a 20 kilogram rifle, and it can fire, that's a big rifle by the way, can fire a 30-gram bullet at a speed of 500 meters per second. So calculate the recoil speed of the rifle. So the recoil speed, so you have the gun here, the bullet has to go this way, so in response the gun moves back. So that's the recoil. At that instance, how fast is the gun or cannon or whatever moving? So before we do anything, the trick with these problems, it's not even a trick, it's just you note something. Before there's any motion, how much momentum does the object have, or the system have? Can't say the object because we have 2 of them. Before anything's happening, nothing is moving, right? You have the gun or the bullet sitting in the gun, or the cannonball sitting in the cannon, whatever. Nothing's happening. So the system has no momentum because there's no velocity. So when the thing happens and the bullet goes flying off this way, the final momentum, so basically what we're saying with the conservation of momentum, if we initially have no momentum, then the P final also has to be 0. Now that is not to say though that after the firing or whatever that nothing is moving. Well, quite the contrary. Both things are moving, but because momentum is a vector, then motion this way could be canceled out. The momentum from the object moving this way will cancel out the momentum of the object moving back. So they're just additive to 0. So this is why the gun has to move back. And so all we're going to do is we're going to note that the final velocity or the final momentum must be 0 of the system. So what is making up the final momentum? Well, it's the momentum of the rifle and the momentum of the bullet. And so we're saying that they will add to 0. Okay, so there's a whole lot of sub-indices here just to keep track of everything, because we have 2 objects and each object has a velocity and each object has a mass. So we have a total of 4 potential variables. And so all we're going to do is we set the momentum of the rifle plus the momentum of the bullet equal to 0. We sub in both of those in terms of mass and velocity, and we solve for the velocity of the rifle. So once you do that, you would have to have, so V rifle would be equal to the negative mass of the bullet times the velocity of the bullet divided by the mass of the rifle. So if you want to lessen or reduce the recoil velocity of a gun, you just make it heavier because it won't kick as hard. So if you have if anybody's, you can go look up, there's a handgun called a Desert Eagle or something. It's some retarded, like, 50 or what is it? I can't remember how big it is, but whatever. It's basically a hand cannon, and I can't imagine what that would be like, shooting a 50 or basically a shell out of a handgun. So the recoil on that would be ridiculous because you have a large mass exiting the gun with the small mass of a gun. But anyway, so you get, after plugging in all that stuff, you get negative 0.75 meters per second. So it's not like stupid fast, but it's not negligible either. Because what has to stop that velocity? Well, your shoulder. So the negative sign simply means that the velocity is in the negative direction, just because we would typically take the projectile velocity to be positive, or that direction to be positive. So that's all the negative sign means. Okay, so example 2. So this is another, anything that starts with negative or 0 momentum and you throw something, there's all sorts of problems you can do with that. So it doesn't have to just be constrained to talking about cannons and guns and all that. So this is true, this problem is true. Okay, so you have to spruce these up a little bit. So let's say you find yourself, you were 80 kilograms in the middle of a frozen pond and you're holding a 10-kilogram suitcase filled with money. I mean, why not? So how long would it take you to reach the shore of the pond, which happens to be 20 meters away, if you can throw the suitcase with a speed of 3 meters per second? Okay, so you might say, oh, well, what's my throwing the suitcase have to do with me reaching the shore? Well, we've already shown that in the last example, that if you're on the ice and you throw an object that way, in response, you will move backwards. So you are the gun. You're throwing the object. And so what the thought process behind this problem would be, you're 20 meters away from the shore. If you're on ice, it's probably frictionless. So once you throw the suitcase, I would probably just keep the suitcase. You will start to move back. Whereas the other problem, that was it. We were done. We found the velocity, that was it. So this one's a two-parter where you'll find the velocity of u after you've thrown the suitcase, and then we're just going to figure out how long it takes to cover 20 meters. So it's the same setup. So you solve for the velocity of u, just we're saying that the initial momentum 0, that means that the total final momentum has to be 0. So that means that the momentum you give the suitcase, your momentum has to be the opposite of that. So you solve for the velocity of u, and you get about negative 0.375 meter per second. So that's the velocity at which you would approach the shore. So now this is now just a kinematics problem. So we solve for the time. We have distance is equal velocity times time. So we want to cover 20 meters, and we're moving at that velocity, that very small velocity. And so that would be 53.3 seconds, which is whatever, call it a minute. So that would take a long time, but it could be done. I sometimes like to do this problem. You could either be stranded on a pond, or you could be working on a space shuttle or something. But anyway, you never know when the situation might call for some momentum conservation. Okay, so the last example is not really a problem per se, but when it comes to, but it's something I do like to ask. So I want to calculate, I could ask the question from example one with the bullet and the gun. Could I have an estimate of how much energy was contained in that mechanism? In this case, I know we're not talking about muskets, but if there were gunpowder or something like that, how much energy was contained within the propulsion mechanism of the gunpowder or whatever? Um, so the short answer is yes, right? Because you could have, initially you have no kinetic energy, initially you have no momentum. At the end of the day, you still have a total of no momentum, but now you do have net non-zero kinetic energy. So where did that energy come from? And the energy come from the propulsion mechanism. So in the case of the gun, we're talking about some chemical reaction or something like sparking a thing, and it releases energy. So that's what leads to the motion of the bullet in the gun. For you sitting on or in example two, this would basically be how much energy did you expend to throw the suitcase, which would have been something we couldn't have answered using Newtonian stuff or even conservation of energy, really. Um, but anyway, so how do you do it? Well, we know the velocities of both the gun and the bullet, so we can easily solve for the kinetic energy of both the gun and the bullet. And so you would calculate that out. It's not going to be exactly the same because you would have some energy lost to heat or whatever, but we can estimate at least. So plugging all that stuff in, you would get about 3755 or about 3760 joules, which makes somewhat good sense. But anyway, so this is just generally presenting the idea of conservation of energy and just getting our feet wet doing a few simple problems. So the next lecture will be even shorter because I just have to at least have told you about center of mass. That'll be the next lecture, and then the final lecture in this series will be collisions. So anyway, have a good rest of your day.